Hi guys, welcome to this sixth video looking at athlete monitoring data. Today we are going to extend the models that we've been running to include a second covariate of training load. So for this tutorial you will need open the Data1 CSV, the interpretation worksheet and the script in SAS. And we'll start in SAS. So far, all we've done is look at the influence of sleep as on the subsequent day daily wellbeing score. We included the mean-centered sleep, so we subtracted each individual's average for sleep from their sleep score for that day, and that gave us an hourly difference from their normal sleep. We put that into the model. And we've used random slopes to see how the influence of that covariate differs between individuals. But sleep isn't the only thing that affects well-being, and one of the most widely researched variables with regards to daily well-being is training load. So given we have the training load data via sessional RPEs, it makes sense for us now to include training load within the model and see the influence that that has. So we've done the same thing with training load as we did with sleep. We've mean-centered it. And to include it within the model as a covariate, all you have to do is add the variable name to the model statement. And so now what we have is it's virtually exactly the same model as before, except now we have accounted for the mean-centered training load as well. And so when we run these estimate statements, the estimate that we get out will now be at the mean training load for that athlete. So if that athlete has 200 units of load as their mean daily training load, that's what it'll be at. If they have 600, it'll be at that value. And so these estimates may or may not be different to the estimates we've got before. I'm going to leave it for you to have a look, compare those two and see if there's any differences. So let's run the model. And you can see class level information is the same. We've still got 27 participants. The convergence criteria has been met, which is good. We have our covariance parameter estimates. And then we have our solution for fixed effects. The random effects are the same as last time. Our type 3 test of fixed effects says that both sleep and load have a significant effect. But if you look at the estimates, 1 unit of load has an extremely small effect relative to the 1 hour of sleep. And that's because 1 unit of training load isn't anywhere near as important as 1 hour of sleep, because we typically work in hundreds and 200s and 300s of load and the impact they have. So if we multiply that by 200, it wouldn't be or 300, it would be closer to the sleep estimate. And then the residuals and everything looks pretty good. Again, we've got a couple of outliers like last time, and we could potentially run some analysis to see if those outliers can be removed, but in general, the residuals look pretty good. So now that we've included training load in the model, why don't we try and get an individual slope for every athlete? So rather than just having their slope account for sleep and be steeper or shallower dependent on how much they respond to sleep, why don't we consider how well they respond to training load as well and have a more complete picture of the slope that they should have? And to do that, again, all you do, just add mcload underscore SAS, which is our variable name for the mean-centered training load, sorry. Add that variable to the random intercept, and then because we have type equals on, what the model's going to do is it's going to calculate the covariance between all three of these variables. So intercept with sleep, intercept with load, sleep with load, as well as the variance parameters that we're interested in. So let's run that model. Check the log. No errors, no warnings. However, the model has not converged. And the model has not converged because of the difference in units that we're using. So because the sleep is 1 hour difference in sleep is much more important than a 1 unit difference in load, we end up in a situation where the sleep overpowers the load and the model can't accurately generate estimates for both variables, particularly when we're looking at the covariance between them. So this leaves you with a little bit of a problem in terms of, we know that 1 hour sleep's important. We could work towards, for example, a 2 or a 300 unit in training load, but it's difficult to know what is equivalent to a 1 hour difference in sleep. So what we can do instead is we can use a paper by Andrew Gelman, who is an incredibly well-regarded statistician, and scale both covariates to a 2 within participant standard deviation change and run the model again. And what this does is this standardizes the differences between participants based on their own individual variation and makes it much more consistent. So in order to do that, you basically perform the z-score formula, but double the standard deviation. So for the sleep measure, what you would do is you will subtract the mean from the sleep for each individual athlete, so each individual's mean from their sleep score for that day, to get this score, the mean sleep underscore SAS score, and then divide that by 2 times that athlete's standard deviation. So for athlete 1, the standard deviation of all of these measures multiplied by 2. And when you divide this number by 2 times that standard deviation, you end up with minus 0.355. Similarly, with the load, you do the same thing. You do today's load minus the average for that athlete, which gives you this mean centered load, and then just divide it by 2 times the standard deviation of all these 91 measures that they've got. And if you do that for each athlete, you'll end up with a bunch of numbers that are a 2 z-score, a 2 standard deviation difference in the load. And doing it in this way is important because what it means is when we run the estimate statements, all we need is one portion of it. Because we've standardized it to 2 standard deviations, we just need a single portion of that value. And what we've done next is, rather than just including the sleep measures, when we're looking at 1 standard deviation below the mean and 1 standard deviation above the mean for the wellness score, we've added load as well. And we've added load to the athletes as well, because we're getting a random effect for them. We can get their individual load differences. So hopefully you can see that it's just an addition of one variable. So the covariate of training load is added to the model. It's then added to the random statement. And because it's added to the random statement, it can be added both before and after this line. So we can get both the mean amount before and then the athlete's adjustment of load after, and use that to get an estimate of the daily wellbeing score for an athlete at minus 1 standard deviation and plus 1 standard deviation. So let's run that model. Okay, so it's converged, which is good. You can check the log, but if it's converged, generally it's worked out okay. And you can see the covariance parameter estimates are much bigger now. So you can see we've got the covariance between the athlete and sleep. the training load and the athlete, and then the training load and sleep. But we're most interested in the between athlete variation, between athlete variation in the effect of sleep on daily wellness, and the between athlete variation in the effect of training load on wellness, and the within athlete variation. We have some fit statistics. We've got the solutions for fixed effects, which again says they're both significant, as does the type 3 test of fixed effects. And then we've got our estimates. So first things first, we can see a 2 standard deviation increase in sleep has about an 8% increase in wellness now, which is much greater than before. And that's probably indicative of the fact that a 2 standard deviation increase in sleep is more than 1 hour difference. Similarly, we can see that a 2 standard deviation increase in train load has a negative effect on the subsequent day's wellness. Again, we don't currently at this point know what 2 standard deviation difference is, so whether this is meaningful or not. And then the intercepts are all much closer together, and there's a reason for that. And the reason the intercepts are much closer together is because we're essentially cancelling out some of the differences with the way we did the estimates. So if we're looking for intercept minus 1 SD, what we're saying is reduce the sleep so it gets worse, and then reduce the training load so it gets better. So one thing you might want to do is you might want to actually look at this with the load switched around. So an increase in load should result in a worse well-being, and a reduction in sleep the same. Likewise, an increase in sleep and a reduction in load should result in increased well-being. So if you want to look at those variables and how they differ, you can see that the difference is actually 11% in real terms, so to speak, when you compare the two differences of the 1SD difference. And you can do that for all the others. All I've done here is just give you an understanding of how you can get some more individual level estimates. We can't plot these because it would need a 3D plot, which I don't have the skill to do, to be completely honest. But we can look at the differences in numerical format. And then finally, the residuals are kind of like before, a couple of outliers, but generally pretty good. So this is the model with training load included. We've had to standardize everything to a 2 standard deviation difference in sleep and a 2 standard deviation difference in training load. I have added the Gelman paper to the GitHub so you can read that paper and understand why we do things that way. But what we're going to do now is focus on understanding and interpreting the model. So if you go to the interpretation spreadsheet, you can see I've copied the covariance parameters in the S and TL covs and the estimates for 2SD plus sleep and 2SD plus load. And as you can see, what we've done is the same as always. We've got the pooled standard deviation. We've got the between athlete standard deviation, between athlete standard deviation in the influence of sleep on wellness, between athlete standard deviation in the influence of training load on subsequent day wellness, the within athlete standard deviation. And we have the individual estimates. Remember, for this pooled standard deviation, this is now a sum of all of the unstructured variables that have the same number. So between athlete variation, between athlete sleep variation, between athlete train load variation, and the within athlete variation, sum those 4 numbers together, then square root them. And we use this to get our effect sizes. We divide the estimate by that number for both sleep and train load, and then we divide both the lower and the upper estimates by the same pooled standard deviation to get the lower and upper values. And we have our p-values for both covariates in F. And these p-values are for a 1 unit difference, which in this situation is now a 2 standard deviation increase rather than a 1 hour increase. So let's see what the results show. And the results show that there was a significant small increase in the subsequent day daily well-being when there was a 2SD increase in sleep. Again, this is a significant p-value, and then your confidence intervals are small. Your effect size is small, and these are your confidence intervals for it. And there was also a significant small decrease in subsequent day daily well-being with a 2SD increase in training load. As you can see, again, a minus 0.2 is a small effect size, but it straddles the border with a lower and upper. So again, it's questionable from the confidence intervals how certain you should be that it was a small decrease, or whether it was a trivial decrease, according to Cohen's d effect sizes. So in summary, a 2SD increase in sleep results in approximately 8% positive change in subsequent day daily well-being, whereas the same increase in training load has a negative response of about 3%. And at first glance, this sounds great. But again, we need to think about what's a meaningful change. And then we need to know what is a 2SD difference for a given athlete and how likely that is to happen. And so what I've done is I've done the 2 standard deviation differences here. So I've worked out the standard deviation first, and then just doubled it. And in doubling those values, what we end up with there now is we have an understanding of how much training load needs to increase in order to get that small difference. And you can see these are really large numbers. So we need a 1,037 unit difference in training load, a 1,037 unit difference in training load for athlete 2. So 1,037 greater than the mean in order to get a 3% difference in wellness, which is, to be honest, quite ridiculous. And you can see that for a lot of these athletes, these numbers are really quite high, whereas for some of them it's more reasonable. Likewise, you can see from the sleep that for some athletes, to get that 8% increase in wellness, they need to increase their sleep by 4.5 hours above the mean, which again seems quite high. So you can really see how, although we're able to standardize these values really well and use them in a model really well, we need to be careful with what that means in real terms for each individual athlete and how likely that is to happen. So now we can go on to the between athlete and within athlete standard deviations, which have remained similar throughout all of the models we can do. We experience them. We can interpret them in exactly the same way as we have done so far. And you can see that there's other factors that we're not considering at the moment that are probably accounting for a decent amount of the variation within athletes, and that might be the reliability of the measure, might be the motivation to answer the questionnaire correctly, or other stresses that we're not capturing. So we just need to be aware that there is still quite a big within athlete variation. And then we can look at the covariate standard deviations for sleep and training load, and we can use them to see any athletes which are responders or non-responders or high responders or low responders to sleep and training load. And we do the same thing to get the typical athletes the typical athlete's response to a 2SD increase in sleep, as we did in the last video, which is just add and subtract the between athlete standard deviation from the mean estimate, which is here and here. Do the same thing for training load for the -3 and the 1.18, which gives us approximately -2% to -4%. But we need to be aware of the confidence intervals of the training load, which are absolutely enormous, and just be wary of the estimate that we actually have there. And again, this shows really nicely how it's a chi-squared distribution and not normally distributed, the random effects. Because if it was normally distributed with a 0.5 lower, this would be about 1.6, 1.7. So potentially it's worth looking at the model fit and deciding from that whether it's worth including the between athlete train load as a random effect within the model. And again, if we want to look at the responders or non-responders in terms of a 2SD increase in sleep and a 2SD increase in load, we again use the estimate statement. And like before, we just take 2SD difference, make sure we include the individuals adjustment for it, and we can do the same for the training load. So this is athlete 9, and we'll see now if athlete 9 is a responder, where athlete 9 would fall within the responses. And here we are. So a 2 standard deviation increase in sleep for athlete 9 would result in a 24.4% increase in daily wellness, whereas a 2 standard deviation increase in load would result in a 4.9% decrease in wellness. We go back to our interpretation. We can see that adding 10.75 to the mean, adding 5.5 to the mean sleep is 13.5, so they respond really highly to sleep. And -4.4 is the worst estimate for training load, and they're above that, so they respond highly to both measures as they increase. What we could then do is we could say, right, we know that that's how they respond, but how likely is that to happen? Well, a 2 standard deviation difference is 500 units, so that probably is only going to happen when matches happen. And a 4-hour increase in sleep is probably only going to happen at weekends, so, sorry, wrong number. It's even worse in that situation, so 600 and 4.95. How likely are those differences to occur? So are they actually high responders, or have they just got extremely variable data? And that is a whistle-stop tour through how to include training load, how to interpret the model. Everything's the same as before, you're just obviously looking at a couple more numbers. And it's important to note that so far we've been looking at the daily well-being score itself as the output measure. In the next video, we are going to look at the change as the output measure. So the change in daily well-being, how does sleep and training load affect the change rather than the score we have the next day itself.